Okay, that seems not to be the case. Then let's dive right in. Let me share my screen. Okay, so the title of today's lecture is Polymorphism and Type Classes. I have briefly explained both in the introductory lecture already, but today we want to take a step back and look at it more slowly and closely. First, one slide on type inference that we also already looked at briefly. So the compiler can automatically infer types for expressions and functions and constants and everything you define automatically. So annotations are rarely necessary. But you can always explicitly annotate an expression with a type. I mean, we saw examples of that with colon type. And then the compiler will check whether your annotation is correct. And as I mentioned, and as I've done in the example code, it's considered good style to always provide type signatures for your top level definitions. And that's basically a form of documentation, because often when you see the type of a function, you already know a lot about it. And finally, as I've also demonstrated in the REPL, we can use :t or :type to ask for the type. And over time, you will need that less and less, but especially in the beginning, it's often useful to ask the compiler and to see whether what you think the type should be and what the compiler says the type is, whether you agree. Okay, this is basically a recap. And now let's start with parametric polymorphism. So generics and other languages that, for example, you define a list type once and for all, and then you can instantiate it for arbitrary element types. Let's first look at an example. So we saw this first function in the last lecture, operating on pairs, which gives you the first component. So first of x comma y is defined as x, and we also had second, which would give you the y. And let me maybe already switch to this. Let me close this. That was last week's. And let's see, where are we now? 4. Just open that. I just comment everything out. So first, right, let me just go into this folder, and then I can open my REPL. Okay. And I mean, it works as advertised. If I have a pair of, let's say, a string and, I don't know, a Boolean, then the first function will extract the first component of the pair. The second one, that's also defined in the prelude, would extract the second component. Okay, so what's the type of that? We have one type here, but you could give many more types. So let's check on the slides. So for example, I could also give it this type. So I could say first a comma a to a. And as we see, the compiler is happy with that. But the signature I gave first was this one. The compiler is also happy with that. So what's the difference between those two? With this one here is more restrictive, because I mean this one says I can have a pair of arbitrary types A and B. So the first component can be is then of type A, the second of B, where A and B are completely arbitrary types, and it will give me the result will be of the type of the first component. Whereas here there's only one type. So I'm no longer looking at arbitrary pairs. I'm looking at pairs where the first and the second component are the same. So if I comment this out again, so if I use this definition and my original example, we saw earlier that that worked. Now gives an error, and this can't match bool with list of character or string. So now it complains that this second component has a different type from the first. Because now I have this type signature, so I still can pick an arbitrary A, but then my pair must have first and second component of the same type. So this is no longer working, but I could do this. Or I can, it doesn't have to be string. I mean, I can also do false true. If both are Boolean, it's also fine. But no longer arbitrary when I give this signature. And I could restrict it even more. So here are a couple of examples. So I could have int comma a or int comma int, or this one, or int comma character. So let's try one more maybe. Let's say so that will still compile, but now this no longer works, because now I say I only looking at pairs where the first component is an int and the second is a character. So I can do 42x, and that will still work. Right, just as a side note, I mean, if I write something different here, for example, I don't know, bool, then that won't even compile, because now I'm claiming that, I mean, I have the x is an int, but now I say I will return a bool, but I return the x, so that's why the compiler now says bool and int are not. So I mean, you can't write arbitrary stuff, but we have now seen at least these three different things that all work and that all compile, but they have different behavior. So the question now is, I mean, first of all, what does the compiler do? Because we said here that there's type inference. So for a given expression like this first, so if I comment all three, it didn't know and reload. We said we can always ask the compiler for the type. I mean, it's already shown here in this warning, but I can explicitly ask for the type of first. And it gives me this one, the one I had in the beginning. So not this or that or any of the others here on the side, but it gives me this one. So the question is why? And maybe from my explanations, you can already guess why it picks this one. This is the most general one. So there's like a partial order between these types. So for example, I mean, some are more restrictive than others. So I had this first line as an example and this one. And with this here, I could still do Kenya and true. But with this one, no longer, because the components were not allowed to be different anymore. So this type signature is more restrictive than that one. So it accepts less input, basically. And this is even more restrictive, or this, for example. I mean, a comma a still allows me to pick an arbitrary type A. Doesn't have to be int, it can also be string. But here I have no choice at all anymore. I need to take two ints. So that some of these are more restrictive than others. And it turns out this one is the least restrictive, the most general type that I can possibly give to this FST function. So I can't make it more general, but this is the most general one. And somehow I already mentioned that the Haskell type system has been defined very carefully, and it has the property that each expression, each valid Haskell expression does have such a most general type. So there is always a unique most general type. So the one that you can use most flexibly, that accepts the most, the most variety of inputs. So it's most flexible in its use. And all other possible types that you could give the expression are basically result from fixing some of the type parameters in the most general type to a specific value. So for example, so this one here is the most general one. And so the claim is all the others can get from the most general one by making certain choices for the values of type parameters. So for example, to get to the second line, I make the choice that B must equal A. So I substitute A for B, and I get this. To get from the most general one to this one, I basically pick A as int and B as character. And then I arrive at this signature. And the fact is that that's always the case. For arbitrary Haskell expressions, there's always a most general, so that all other possible ones are specializations of the most general one, in the sense that I fix the values of certain parameters. And not only that, so that's one property of Haskell expressions, or the Haskell type system, that every expression always has a most general type. And on top of that, it's not only there is such a most general type, but the compiler can also infer this most general type. And I mean, we see this in the REPL. When I ask for the type, it gives me this most general type. And we also see it in the editor. So the editor also uses the compiler under the hood. So I basically, it just suggests the type. So I don't even have to give the signature myself. Right. And as I also mentioned last time, here what's said in the parentheses, there are language extensions that are not pure Haskell, basically, or not standard Haskell, where this is no longer true. And in the lectures, we also see examples where you really do need to give type annotations to help the compiler. But vanilla Haskell, standard Haskell, has this nice property. And I already told you this. So if we take this most general one, then we get all the others by instantiating A and B, A and or B to more specific values. So we get this one by setting B to A. We get this one by setting A to int and B to character. We would get this one by setting A to this type, functions from A to int to B, and B to C. Okay. That's that. Okay, one remark, Haskell terms carry no type information at runtime. So at runtime, I mean, this is just for compilation. The type checker works and all these types are there. So at runtime, all that information is away. And one good question is, or one source of confusion is sometimes who is going to pick at which time to use that. And that's always the caller of the function. So somebody implemented this first function here. And now in the REPL, I'm the user of this function, and I can decide. So for example, I can do right this. I mean, that was just a warning. Let's go back to that one. So I, as the caller of first, now can decide I want to use the first function for A is of type string and B is of type bool. So I am to decide. So basically it's like a contract between the implementer of the function and the user. So the implementer, when he writes a function with a signature like that, it says you as the user can pick arbitrary types A and B. and my function first will work for it. So I, as the user here, picked Kenya and true, so string and bool, and used it for those types. And sometimes, I mean, you might wonder, I mean, I already demonstrated. So if I restrict that, so if I'm not using the most general type, but the more restrictive one, then I mean, that works in the one direction. So the same implementation still works, but I have less flexible use. So, I mean, I can demonstrate that as well. This example, so restricted first. So let's say int comma int to int. So I can define it like this. This is okay because now this restricted first is basically the user of this function. So the user gets to decide what A and B is. So here I decide A is int and B is int. So that's fine. First works for any choices of A and B. My definition of restricted first, I can make the specific choices to use it for A and B are both int. But the other way around wouldn't work. I mean, this is here on the slide. Maybe I don't type that. So if we try to give a second implementation of new first, again with this general signature, sorry. And if I define it as restricted first, then I get an error. The error says couldn't match type A with int. So here I'm claiming that I can write a polymorphic function for arbitrary pairs of arbitrary A and B, but I try to use as definition my restricted first, and the restrict first only works for int. So that's why the compiler is complaining in this case. So the lesson here is you can always use the more, I mean, the more general type, something with a more general type in a restricted situation, but not the other way around. If you have something that only works in a restricted situation, you can't use it in the general situation. So you can always narrow the scope, restrict the type, but you can't expand it. Which is one reason why normally by default one always works with the most general type, because it has the most flexible use. You can use it in most situations. It doesn't cost me anything. I mean, I always only have to write this one line of code. But if I basically use it at the most general type, then in many situations for many specific choices of A and B, I can use it. If I wrote my function like this from only int, then if I want to use it in a context where I have a pair where not both components are int, then I wouldn't be able to reuse this function. I would have to write a new one. Whereas if I start with this most general one, then it's useful in most situations. Therefore, normally people write, I mean, give the most general type. Sometimes there are situations where maybe it makes sense to give a restricted one, but as a rule of thumb, basically always use the most general type. So I have to comment that out, otherwise I have error. Right. And these types, like pair of A and B, I already mentioned that, are parametrically polymorphic types. So I think polymorphic is Greek, or I mean ancient Greek, and I think morphic is shape and poly is many, so many shaped. So types like this that have at least one type variable are called polymorphic types. And these type variables can be instantiated to arbitrary types, but you have to respect that you can't, I mean, the same variable has to be instantiated to the same type. So we saw this here, for example. I mean, I can arbitrarily pick A and B, but once I have picked A, the return type, I can't choose something else here. I mean, if the first component of my pair is A, then the result will also be A. It can't be anything different. Obviously, because I mean, the first component is what it is. And okay, where were we here? And if a function, if you are defining a function, a polymorphic function, or any function, and if one of the function arguments has a polymorphic type, then you don't know anything about it. I mean, it could be an arbitrary type, so you have no information about what the type is. You can't make any assumptions. And if a function result has a polymorphic type, and because you don't know anything about that, the only way to somehow write the function is to make use of the function arguments. So we can look at an example. This is, I think, actually quite nice. Not sure what I called that here. That also doesn't matter. Foo. Okay, so let's try to write a function from a pair of ints to int. So we have y are ints. I should switch off Copilot again. But I mean, the one suggestion it made, I can do. So Copilot suggested x plus 1. I get this warning here because I'm ignoring y, so I can replace it with an underscore. Just give me 1 second. Sorry, just 1 second. I must just plug in my laptop. Okay. Okay. Right. So this is certainly one option. So let's reload and see. Foo1 of 42 and 5, for example, is 43. So it takes the first component of the pair and adds 1. Can somebody give me a different function with this signature? So can somebody suggest anything else that also has the signature? It takes a pair of ints and produces an int.
X plus Y.
Yeah, sure. That would work. Thank you. So let's try Foo2 and 47. And maybe one more. My keyboard sometimes acts up. One more suggestion.
X times Y.
Yep. Okay. Right. And I think now you believe me when I say that there are basically infinitely many functions I could write that have this signature. I mean, there's arbitrary stuff I could do. I mean, I could also, let me write one more. I mean, just to demonstrate that. So I don't know why. I mean, I can do crazy things like whatever. Right. And I mean, this makes it obvious, I hope, that there are the infinitely many possibilities, or maybe not infinite, but like a very large number of potential functions I could write that have this signature. So that means the signature doesn't tell me much about the function. If I just know the signature, if you tell me, oh, this function takes a pair of ints and produces an int, then I have very little information about what the function actually does. I mean, it could be any of these foo functions. Okay, but now let's look at different signature. Or I see I made a mistake. It was supposed to be int, int, but it doesn't matter. I mean, I don't know whether it's important to be consistent with the slides. I mean, we can just fix all of these. Okay, same story. I mean, there's even more possibilities. I mean, not really. I mean, still infinite. Right. So the point is, with signature like this, we basically don't know anything about the function. I mean, it does have this type. That's already information, but we don't know anything about how X and Y are used to produce this result. Okay. And now I have these pairs. But same idea. Fine. Okay, so now let's look at this. So bar polymorphic type from A comma A to A comma A. I don't like this anyway. So I have X and Y. So now can somebody tell me what I can write now? Make a suggestion. So it's the same thing. I mean, I take a pair of A's and must produce a pair of A's, but now I don't know anything about A. In the first example, I knew I had two ints. Now I just have two values of type A. I don't know what A is. It could be int, of course, but it can just as well be string or bool or anything. So can I write such a function? Can somebody give me one?
We can return the same
Yes,
pair.
that's one option. So that works. And now, I mean, I can do whatever. I mean, bar. I mean, if I can use ints, I need to. And it returns the same. I mean, it's a bit boring, but I mean, it also works for. Right. So that works. Very good. Anything else I can do?
We can switch the variables.
Very good. Yes, we can do that. Okay, that was my bar one. And now switched. Yeah. And I tried with numbers. It also works, of course. Okay. Any other option? Anybody?
We have in the chat.
Okay. Should I check or can you just tell me what's in the chat?
We have X plus Y and X plus Y.
Okay. And the compiler is not happy. And it basically tells me, I mean, plus is a method of the int num class. So it tells me I don't know anything about the type A, so I don't know whether you can add two A's. I mean, for example, A could be Boolean. What does true plus false mean? So that doesn't work because we assume that you can add two A's. I mean, for int it would work, of course, but now we don't know it's int. I mean, it could be anything. So that doesn't work. Any other options?
We have x equals y.
X equals y,
Yeah.
like this?
Yeah, he used an assignment operator, but I think he meant equals.
Okay. Well, this is a Boolean. First of all, we don't know whether you can compare A's for equality, but even if you could, it wouldn't have the right type because we need a pair of A's and this would be a Boolean.
We
I
can
mean,
have
let's,
a
yes,
we can have a pair of y's and a pair of x.
yes, exactly. In which case, I mean, I don't really need this anymore. Okay. Oh, sorry. Exactly. So that works. Are there any more options than those four? Now it's a pity that we're not in a classroom. We could have a vote who believes there are more and who doesn't. But actually, this is all. And I can prove it to you because I want to write such a function as it said on the slide. I mean, I must produce a pair of A's. So I must produce two A's here. But I don't know anything about A. I can't add stuff. I mean, I don't know anything. It's just a type, but I don't know what that type will be. I mean, when the caller calls it. So the only way for me to produce an A, because I don't know anything about the A, is to somehow make use of the arguments of the function. So in this example, that's the X and the Y. So all I can do is somehow use the X and the Y on the right-hand side. Okay, so I mean, I need to produce an A twice. I mean, for the first component, the second component. So let's just look at the first component. So I need an A here, and all I have at my disposal are the two A's that are given to me as arguments to the function. So I can pick the one or the other, but I can't combine them like I did here because I don't know whether it's like A is num, so I can add it or anything. So there's no way for me to combine X and Y to a new A. All I can do is pick X or Y. And because I have the same choice for both components, that gives me four possibilities. And we now have all four here. The first can be X or Y, and the second can be X or Y. So in total, there are only four possible ways. So those four bar functions here are the only four functions that have type signature. If I ignore the fact that I could loop. I mean, I could also write something like bar 5, bar 5. That would also sorry. That would also compile, but this bar 5 function is an infinite loop, so that doesn't give me a result ever. So this is always an option. You can always do something like that. But if you insist that your function is we call total, so for all like inputs it produces outputs, so it doesn't crash, then those four are the only four possibilities. And now last example, bus a comma b b comma a. Okay, can't somebody give me a possibility here? So I have an X of type A and a Y of type B, and I must produce a B and an A, and I don't know anything about A or B. So what can I possibly do?
We have in the chat a pair of Y and X.
Okay, exactly. I mean, this works. I have an X and a Y. Y is of type B, so I can put it here because a B is expected there. And for the A, I can pick the X. And I mean, with the same logic that I used before, this is now the only possibility. I can't do stuff like XX anymore because I don't even know whether, I mean, A and B could be the same type, but don't have to be the same type. So XX, for example, like here, bar 4 wouldn't work here because that would assume that X is simultaneously type A and B, which I don't know because A and B are arbitrary types. It could be string and int, for example. So yes, so in this case, for this signature, there's only one possible implementation. For this one, there were 4, and for this one, there were infinitely many. So that somehow, I mean, it's not a mathematical proof, but it should give you an intuition that the more general the type is, the fewer implementation options you have. And sometimes in extreme cases, like this bus case, there's only one option. I mean, of course, there can also be no option. So actually, this, what should I call it? Weird also. So for example, for this, there is no option because I would, out of thin air, need to conjure a value that's of arbitrary type, and such a value doesn't exist. I mean, in other, I mean, if you had other type systems, like in some languages, maybe you could write null or something in object-oriented languages, but we don't have null in Haskell. So this doesn't exist. So the only thing you can do is basically write defined or error. So the only function with this type signature is one that crashes. So you can't write one that doesn't crash and gives you a result for, because for arbitrary type, you don't know what A is, and you can't write anything here that is of any arbitrary type. That is simultaneously, for example, int and string. I mean, you can write something like this, as we have seen, list of A's, because then you can use the empty list, for example. Or we can write something of type maybe A for every A. I could write nothing. Sorry. But this doesn't exist. Okay. Right. So the lesson is that the more general the type, the fewer implementation options. And in some extreme cases, there's only one or very few. And that means it actually makes life easier for you as the programmer if the type is more general. I mean, you can basically make less mistakes. I mean, here, if you need this function, the compiler can't help you very much. I mean, you have this infinity of possibilities, and you somehow must pick the right one that you need at this point. But here, you need no creativity, or I mean, you don't need to know anything. Basically, you can just fully trust the compiler, and once the compiler is happy, you know you have found the one and only implementation. That's one reason. Another reason why, I mean, the first reason why we like general types is because they're more flexible. So you can use a function with a general type in more situations than if it had a more restrictive type. But the second reason we like general types is because they make programming easier, because they take away possibilities and restrict you to, I mean, allow the compiler to help you more. I mean, for example, in this case, if I do this, I mean, use these holds and reload. So I get, let me make this a bit bigger. That's here. So I get errors that I have holes in my code. But then if I read, then it says valid hole fits include Y. So I can just put the Y there. And if I continue for the second hole, it says valid hole fits include X. So the compiler, without me having to do any thinking, it already gives me the only possibility, the only thing I can do here. And if I do the same here, then hopefully, yes, now it tells me valid hold fits include X or Y. So we see that, I mean, now there are more possibilities, but I could still, by just following the compiler suggestion, I would find these 4 implementations again without any intelligence on my part. Right. So I think that's quite a nice example. That, I mean, it's maybe somewhat paradoxically, I mean, if you haven't seen polymorphism before, then you might think it gets more complicated. The more polymorphic a type is, the more type variables you have, but actually it gets easier. You just have less things to work with, which makes it easier to see what you have to do. Let's go back to the slides. I think, oh yeah, that's somehow Deutsch Svietstra. Okay. I think he's at Utrecht University, professor of computer science. Okay, so I think I said most of that already. So parametric polymorphism can severely restrict how a function can be implemented. So it's a good thing. So the more general the type, the easier it becomes because it prevents you from making errors. I mean, if with this int thing, I mean, you have a lot at your disposal. You can use constants, you can use plus, multiplication, subtraction. You could do other arithmetic operations. So you have a lot of choices and it's easier to make a mistake. Here, because you don't know anything about the types, there's no operations, there's nothing like addition or anything that you know about A or B. So it makes it very easy and obvious what you have to do. And you also know, I mean, without looking at the implementation, no matter how the function is implemented, it can't possibly inspect the values because, I mean, as we saw, I mean, because at implementation time, you don't know anything about the type. And you can actually deduce properties of functions by just looking at their signature. And that is called parametricity. So one can make these things mathematically precise. So there have been publications about this type of thing. So for example, map, that takes a list and maps a given function over all elements of the list. So takes a function from A to B, list of A's, list of B's. And I mean, we know how it's implemented, but by just looking at the signature, I mean, if you think you want to implement this function, and you don't know anything about types A and B, so as the implementer of this function, you have this function from A to B, and you have a list of A's, and you are supposed to produce a list of B's. So of course you could give the empty list, for example. But if you want to actually write a B down, because you don't know what B is, and you have no B as an argument to the function, all you have is a list of A's and this function. So the only way to get a B is to take one of the A's in the list and apply this function to it. So even, I mean, without knowing anything about the implementation, you know all the B's in the result will have been produced by applying the given function to one of the list elements in the original list. That doesn't mean there's only one way to implement map. I mean, as I said, you could do something like, I mean, you can still do things like, let's see, map prime. So if you have a function like this, let's call it, yeah, I don't know. So I mean the like the standard implementation is this one. We probably saw it last week. So the empty list gets mapped to the empty list, and if you have a non-empty list, then recursively, I mean, you apply the given function to the head and recursively apply it to the tail. That's how it's actually defined, the map we all know and love. But if you, I mean, you can do other stuff. For example, you could do just map everything to the empty list, for example. That's boring, of course. So if we don't want to map everything to the empty list, let's try to come up with something that doesn't map everything to the empty list. So, I mean, you have to look at the, I mean, we can't look at the F. I mean, the functions are opaque. We can't inspect them. So the only thing we can do is splitting cases on the list. So we, no matter what we do, I mean, if we don't want to do this, so we have these two. And now let's first look at this. So we are supposed to produce a list of B's in this case. And all we have is this function from A to B and this list of A's, but in this case, it's the empty list of A's. So there is no A anywhere. We have no A. All we have is this function from A to B, but we can't apply it to anything because we don't have an A. So there's nothing we can do. There's no possible way to produce B. So in this case, I mean, all functions with this signature must map the empty list to the empty list. Okay, and in the second case, I mean, we can do more. I mean, for example, we could, like for map 1, we could set to the empty list. And we can also do other stuff. I mean, for example, we do something like whatever, fx, fx, let's say. But no matter what I do, I always, in order to write anything here, I mean, like here, I always have to apply the given function to an A, which comes from the given list. So this property, I mean, I can do crazy things here, but I can't break that property. All the elements here look like F something, where that something comes from the input list. And as I said, no matter what, the empty list will always be mapped to the empty list, because there's no other way to get a B from somewhere if I don't have an A. So that's quite interesting that by just, I mean, in some cases, by just looking at signatures like this one, we may not be able to narrow down the implementation like in this bus case where there's only one possible way. But nevertheless, we can already deduce facts about such functions without looking at the implementation. So in this example, we know that whatever, no matter what we do, like if we have, if we call it mystery, A to B, A, B, we know we know this must always hold. Let me just, I don't know. Because we can't do anything else. We can't produce a B here if we don't have an A. And there are, I think, various other examples. So as it says here, I mean, this is what we know. We don't know if there are B's, we don't know in which order and so on. I mean, the classic map function, of course, maps the function over every element in the original list. I mean, just looking at the signature, we don't know that. So there's some things we don't know by just looking at the signature, but there are also things that we do know. Like, for example, that the empty list must be mapped to the empty list and that all B's in the result list must be F. I mean, this function applied to something in the original list. Right. And there's this confusion sometimes. So, I mean, if you're a beginner, so you might want to write something like this. So you somehow want to write a parser, like it accepts user input, let's say. So the user types in some string and you want to pass it to different types. So for example, you want to write pass of the string false is false Boolean and pass of the string 0 is 0. But that won't work, so I can demonstrate that. So now it complains, the compiler complains. I mean, apart from the fact that I only have 2 cases here. So let's say, I mean, sorry. We can get rid of that problem. I don't know why my keyboard, sorry, this. Let me just say, okay, but it's still complaining. And now it says couldn't match expected type A with actual type bool. So, I mean, somehow people make the mistake that they think if they write something like that, they can basically return different result types from a function. But remember what I said earlier, the caller of the function can pick an A. So if I call the pass function, I could, for example, say I want A to be int. And then this is obviously not type correct because false is not of type int. So this won't work. Nevertheless, of course, often, let me just check. So let me just repeat this, what I just said. I think it's on the slide. So it's always the caller who can pick the types. And if you have a function with a polymorphic result type, like here, it's impossible to write if you, as I said before, if you don't have any A available on the left-hand side, you can never produce one, except if you crash. I already said that. So now that's that. So this won't work. But nevertheless, I mean, the original intent was a legitimate one. I mean, let's say you want whatever. I mean, you want to accept user input, you want to read from the keyboard, and then you want to, I mean, if the user enters something like false or true, you want to return a Boolean. If he enters a number, you want to give him a number. It won't work like that for the reasons we discussed, but nevertheless, I mean, that's a legitimate thing one might to do. And one way to basically do what you originally intended is to use the either type, which we haven't talked about yet, but that's also a very important, commonly used type that's also in the standard libraries. And so that's also in the prelude. So it's defined like this. So it's polymorphic in 2 type parameters, either A, B, and it has 2 constructors. It can either be a left A or it can be a right B. So the constructors are called left and right. So for example, in the REPL, I can say left Kenya, and that can be of type either string, say bool, and the compiler accepts that, and I can say right true. It's also of this type. So if you have like 2 possibilities, then the either type is your friend. It's in some sense dual to pairs. So pairs is if you have an A and a B, then the pair type, I mean, if you want to, from a function, you want to return an A and a B, then the appropriate type is the pairs of A's and B's, where you can give an A and a B, and either is like or. So if you want to return A or a B, then you can use the either type. So one option to get this pass, I mean, closer to what it's intended to do would be instead of return type A, give it return type either bool int, for example. Then in this case, we could return left false, and in this case, we could return right 0. And now it actually compiles, and I can pass false. That gives me a left Boolean, and I can pass 0, and it gives me the right 0. So that's one option. Another option is to define a custom type. So, for example, you can say, I define a type that, for example, I call value. What is it here in this? It doesn't matter. What does it call here? Sorry. Let me derive show. So I can also use my value type here. Then it would be value false, and here it would be point. Basically the same. It's like either but specialized to bool and int. And this is actually quite a common approach in Haskell libraries, because often you have to deal with untyped languages. So if you, for example, take JSON or XML or something like that, maybe JSON is a good example. There's a very commonly used library on Hackett called ASON, which is for working with JSON in Haskell. And they, of course, face this problem. So somebody gives you an arbitrary, a valid JSON, and you want to pass it into a Haskell type. And of course, there are many possibilities. JSON has strings and booleans and numbers and also lists and objects. So you need some type to express all these possibilities. And therefore, in the ASON library, there's a type that's incidentally called value, because it has much more options than this. And then you can pass a JSON string into this value type. That's here. So that's common to somehow bridge between dynamically typed languages like JSON or SQL to Haskell. Right, and I think now is a good time after 1 hour to have a short break. But are there any questions at this point?
Not in the chat.
Okay, so after the break, so this was what I wanted to say about polymorphism, metric polymorphism. And after the break, I want to talk about type classes, which is a different type of generics, basically, in Haskell, of overloading, or it's called, whatever. We have seen show, eq, and so on, but we want to look at type classes, how to work with them in more detail. Okay, let's say until 1:15.
Yep.
Okay.
Okay. Okay, shall we continue? Are there any questions?
Not so far.
Not so far. Okay, we switch back to the slides. Right, overloading. So also sometimes called ad hoc polymorphism. So parametric polymorphism allows you to use the same implementation in as many contexts as possible. So we saw we had one implementation for the first function, for example, and then we can use it in various contexts like string, bool, or int or whatever. And overloading, also sometimes called ad hoc polymorphism, allows you to use the same function name in different contexts, but with different implementations for different types. So the difference between the two is that here same name, same implementation, and here same name but different implementation. So it's like reusing code. So polymorphism allows you to reuse code, and this overloading is reusing names. So you don't want to like always come up with a new name for stuff that does similar things. So you can reuse the same name. Okay, and that's in Haskell, that's done with type classes that we already briefly touched upon. So, and in other languages, I mean, type class is unique to Haskell, but it's similar to what other languages call interfaces. And interfaces can be implemented for potentially many different types. So one example is the eq class. Sorry, just want to see. So it's defined like this. So maybe I should actually, it's always a bit painful. Let me hide eq. Okay. Right. So the syntax is class. It's a keyword we haven't seen yet, or at least not used yet. So eq a where, and then in the case of eq, we say we want this and sorry, and this is in Haskell means not equal. So in other languages, often it's like less than, greater than, or exclamation point equals, but in Haskell it's slash equals. Okay, so that's basically we define an interface, which in Haskell is called type class. The type is eq for type A, and the type A or a specific type is an instance of this class if we can implement two functions with these signatures. One is called equals equals, one is called slash equals. So equals, non-equals, that's the idea. So how would you do that? So the syntax for that, let's say we want to make bool an instance of this, then we could say instance eq bool where, and now we have to implement those two functions from bool to bool. Sorry, I made a mistake. The result type here is bool. I mean, you compare two A's and it's true if they're equal and false if not. And here it's true if they are not equal and false if not. Sorry about that. So in this case where A equals bool, then of course it's bool to bool. And now we must implement that. So how do we implement that? Well, we can, so for example, say false is true, true is true, and everything else is false. And we could also implement not equals, so sorry, same signature, Okay, false, false, false. Or we can also, actually, we can be smart and just say x not equals y. We define it as not x equals y. And why do I get this? Because I thought I hit everything. Okay. Right, and now if I reload, and then I can try that. Okay, so that's basically the new syntax we learned today for this. So you define such a type class with the class keyword, then the name of the type class, capital, like other types. I mean, even though it's not really a type, it's so-called constraint, but anyway. And then type variable for the type that this instance is for, this interface is for, this class is for, and then you can have one or more so-called methods, and you just give the signature. And then and it's really like an interface in other languages. And then to implement this interface for a specific type, so you make that type an instance of the class, and then you just for this type must implement those functions that are given in the signature. So that's really like interfaces. So I hope that looks quite familiar. And now I could do it for a different type. Unfortunately, it's not so easy if you don't have the built-in equality. But anyway, let's check on the slides. Okay, so that's the first thing. And I did this for bool. Right. That's one typical case. So you just implement your class for a specific type. Now we can also do stuff like this. That's quite interesting. So we can say something like, right. So what does this mean? That means if I have an instance for, each instance for type A, then I also have an instance for lists of A in this example. So the instances that I write don't have to just be for like specific types. I can also basically give these rules that if I know some instances for some types, then I can deduce it for other types, or I can derive instances for other types. So what that look like? So in this case, it says if I know how to compare A's for equality, I can also compare lists of A's for equality. So what would that look like? So signature now is, so I have two lists of A's to pool. Okay, and so what do I do? How do I compare two lists? Well, I must pattern match on the lists. So I have these four cases basically, that one is empty or not, and the other is empty or not. So let's start with the empty list case. So both lists are empty, in which case they are obviously equal. So what if one is, if both are not empty? So what can I do then? Well, I can compare the first elements. So for these two lists to be equal, the first elements must be equal, so the heads must be equal, and the tails must be equal. So I can write that. So I can do okay, and now there are two other cases, but in those cases the lists are not. Sorry. What is the problem there? Yeah, okay. Come to that now. Just want to fix my formatting quickly. The non-equal case, I can again define like before. I can just say two lists are not equal if they are not equal. Okay. So, and now let's look at this equals here and at that equals here, which we needed in the definition. So why was it okay to use this? So here x, y are of type A. And why am I allowed to compare them for equality? Well, because that's what I have stated here. I'm writing this instance for lists, assuming that I know how to compare elements for equality. So this condition here, I make use of when I write this, because x and y are now of type A, and I can use the equals operator here because I was assuming that I can. Now this equals x's and y's are the tails of the lists. So this is recursion. So I'm defining equals for lists by using itself. And we have seen that functions on lists are often recursive. So I need this assumption that I have equality for a's for this, so that I can write that. So if I remove this here, then the compiler would complain that I don't know how to compare a's for equality. And now we can try that out. So for example, now I can say this because I have it for bool. So now I also have it for lists of bools. So I can, for example, now see that these two lists are equal, but if I do something whatever, then not. Right. So that's that. So often, and you can also, if you check on Hackage, for example, let me do this briefly. We do prelude Hackage. Let me just look for. Why does that not work? Wanted to look for eq. Bit tedious. Let's see. The type classes here. Okay, if we look for at the e class in Hackage, then we see the definition, so eq and this equals and not equals here, and we also get a list of instances. So we see a couple of types that implement the eq class. So probably bool is also somewhere in this list. So it's a very long list. Doesn't matter. Somewhere there bool will be. And okay, and then we also see things like what we just did. So whatever, we don't know what zip list is, but something like what we just implemented. So if we know quality for A, then we also know it for zip lists of A. And somewhere there will be this thing that we just wrote for lists. Here we have it for mail here. So this is basically what we just wrote. So that can often be useful if you encounter a type class where you're not sure or haven't seen before. So the documentation often tells you, these rules, and then you know for which types you have that. And that's also something, if I ask for information on this class, then, it gives me the definition, but it also gives me these instances here. So even in the REPL, it's easy to get an overview over the instances that are available. Okay, now let me go back to the slide. So we did this. I explained that this is where we need our precondition. Right, and this is called a class constraint, and we have seen that before. And basically, instances of a class are a subset of all possible types. So not every type in Haskell is an instance of our eq, for example, eq class, but some are. So we have the subset of all of those that are actually instances. And in a type signature that we have seen before, this is indicated like that. So this means you have this function equals from A to bool, but only under the condition that A is an instance of eq. And this is called a class constraint. So this function is this class constraint. So given that A is an instance of eq, the function has type A to bool. And I mean, the eq itself has this class constraint. So if we ask for the type of eq now, of equality, then we get this class constraint. But we can, I mean, there can also be other functions that have class constraints. For example, we can write a function all equals. The idea is to check that whether all elements in a list are equal to each other. So how would we implement that? So again, we must distinguish, is it the empty list or not? So if it is the empty list, then yes, all elements are equal because there are no elements. And if it's not the empty list, so what do we do? Okay, so now it's a bit interesting actually, because if it's, I mean, normally we always have these two cases, but I think in this case, we need three. We must also look at the case that there's only one element, in which case it's still true. If there's only one element in the list, then of course it's equal to itself. And if we have more than one, so at least two, then what's the condition that all of these elements are the same? Well, the first two need to be the same. And recursively, the tail must be all equals. And now if I just write it like this, I get an error here. It tells me that I'm comparing X and Y, which is of type A, but I don't know that I can. So I need the constraint that I actually am allowed to compare elements of type A for equality. And then this compiles. And I can, of course, try it out. So I can say all equals whatever, true, true, true. That's true. But if I change one, then it's false. Okay, so that's this remark. And I mean, we have seen examples of this before, like lm to check whether an element is given is an element of a list, or lookup for our lookup tables there we also needed this eq constraint. And there can also be multiple multiple constraints needed sometimes. So let's look at this example. So if I have example, so I want something like this. So a pair of an A and a B and a pair of another pair of an A and a B. I want to produce a string. So if I have X, Y, Y1 and X2, Y2. I mean, maybe we should just first look at the slide, otherwise my editor will cheat and give it away. So we want to implement this function. And two cases, if x1 equals x2, I mean, this makes sense because both are of type A. And if y1 equals y2, we want to show x1, and other ones, we want to return the string different. And can somebody tell me what constraints we need for this to compile? At least one. I mean, what things am I using that I mean, I don't know anything about A and B. So, and I'm using stuff here that I can't use for all types. Does somebody have a suggestion what constraints I would need?
The equals. as the
Yes,
interface.
yes, for which type? For A or B or both?
For both, I think so.
Exactly. Yes, because I'm comparing X1 and X2, which are of type A. So I need it for A because of this equal sign. But I'm also comparing Y1 and Y2, which are of type B. So I also need it for B. So I need eq A and eq B. Right. So I definitely need equality for A and for B. Let me write this already. Okay. Start writing the implementation. Okay. So, I mean, if I write undefined here, so this is fine now, this compiles. So for the x's, I mean, for the equal signs, we indeed, and if I dropped one of those, so for example, if I don't have this constraint, if I leave the first constraint, then the compiler complains here because I'm comparing the x's, but I don't know that I can. And if instead I drop this eq b constraint, then the compiler complains here because I'm comparing y1 and y2 of type B. So I really need both. Okay, but if you look at the slide, now we do this show x1. So I must, and show, if you remember, it takes a value and converts it to a string, but you can't do that with arbitrary values. There's another constraint here, show constraint. So if I just write it like on the slides, then I see that I need a show constraint on A because x1 is of type A. I would also need show A. And then this compiles. And then I can use it, for example, I mean, for the problem now is, I mean, because I hit the original, so we have very few examples for eq. But bool, for example, does it. So bool and list of bool. So I can apply it, for example, for bool and list of bool. So I can say true. What's true? True. What's true? And it tells me true, which is show of x1. X1 is true, and show of is this the string true. And otherwise, I mean, if I do this, I get different. But I can't do it for a type where I don't have this quality constraints. So for example, right now I can't do it for X and Kenya and yeah, because I don't know that I can compare characters for equality. Of course, I can compare characters for equality, but I have hidden that. I mean, I explicitly hid that in order to do this example. So if I use the prelude, then this would work, and I could do this. Okay.
Lars, we
Yes.
have one answer in the chat that may be good to discuss. Someone proposed equality of pair A and B.
That's an interesting remark. I think logically it's correct. I mean, right. So now I get a word of pain. I mean, one is some stupid thing that for some reason this is not, that's frowned upon. But this remark there, non-type variable argument in the constraint. So in vanilla Haskell, you can't write something like eq a comma b as a constraint. It must always be one type variable. However, that's silly, and that's why there's an extension in GHC for this. And if you read, it says perhaps you intended to use flexible context. So we can, I mean, we already have this pragma here, this, by the way, is an extension that allows me to write signatures. In my instance declaration, I wrote the signatures of the functions here and here. And in vanilla Haskell, you can't, which is stupid, in my opinion, because, I mean, everybody always gets taught that you should, for documentation purposes, give signatures at type level, top level definitions, but vanilla Haskell forbids that. But there is an extension, I mean, this instance 6 language pragma that allows me to write that. And now what the compiler is telling me, if I do this, then I need another pragma. So in my editor, I can just do the quick egg flexible context, and then it's there. So this now goes away, the problem, but it still complains because the compiler doesn't know that if I can compare pairs of A and Bs for equality, that implies that I can also compare A's for equality. We know that that's the case. I mean, we don't really know, but we suspect that the instance for pairs is written similar to the instance for lists by just comparing the first, second component. So we know it wouldn't make sense really to have an instance. I mean, one should think that this implies that you can compare A's and B's, but it doesn't. However, I could fix that by writing this instead. And then it compiles again, and then it's fine. That would do the same thing, because the equality on pairs, I mean, we haven't done this, but I mean, we could, same as for lists, we could do instance eq A eq B. Although actually, I'm sorry, I probably said the wrong thing. Let's just do this quickly. Right. I think I said something wrong. We'll come to that now. So how do I implement this? Well, exactly as we did there. Well, when is the pair equal? If the first and the second components are equal. So x1 equal x2 and y1 equals y2. And this I can again say I mean, I don't want to pattern match, so I can just say I don't really want to call it x and y. That's confusing, I think. Let's call it, sorry, I can call it xy1 and xy2. Not. Okay. Right, and now, I think now if I turn that back to what it was before, that is a bit that's weird actually. Maybe not. No, sorry. So it still doesn't work. Even though now one should think that, I mean, now there's this rule here that, I mean, I know if I have equality on pairs only if I have eq A and eq B, but the compiler still doesn't believe that I can do this. So I still have to compare the percent in this case. So it was right what I said before, but it's a bit strange. But anyway. What's this now? Okay, so it's complaining, but it works. Right. So normally it's better. But if I do this, now this works. That's actually interesting. I mean, because here I'm comparing pairs of A and B, but I only say I know how to compare A's and B's. But now the compiler takes this instance declaration into account and knows that because I have eq A and eq B, I also have eq A comma B, which I'm using here in this changed implementation. So this now works and with these constraints here. And if I remove this here again, then that would no longer work because now it doesn't know, and I mean, it knows I can compare A's and B's, but now it doesn't know anymore that that also means I can compare pairs. So this is really needed here. I want to write it like this. If I write it like that, then it's of course fine without this rule. Okay, that's that. Okay, you could infer the constraints, sort of. Right, now another thing. I mean, this inequality, we always have to define that because it's part of the class definition. But we always basically did the same thing. We just said, why would I go through the trouble of like defining inequality if I have already defined equality? Why can't I just use that? So we have said, well, we just reuse equality and use not logical negation. We have done that for bool, we have done that for our lists, and now I've also done it for the pairs. And that's a common situation that basically you have one class method that you can implement in terms of another. And so actually we can extend this here with so-called default, and I always forget the syntax, right? So we can write x not equals y, x equals y. So we can define this here in the class definition. We can even do this as well. So sorry, that's of course wrong. It's not x equals y, and we can even do the same for the other way around. So we can define. Why is this now complaining? It gets confused with the built-in one. Anyway, so we can do that, and this is a so-called default implementation of these class methods. And now we can remove this here. So now if we don't give in an instance declaration, if we leave out methods that do have default implementations, then that's okay. So if I don't explicitly define inequality in this example, it will just use the default implementation for it. And I could also, because of this one here, I could also just define inequality, and then it would use this to define equality. Of course, now that also means I could leave both. So that would now compile, I think. It does compile, but now, of course, if I try it out, I get an infinite loop because now it, I mean, it only has default implementations now. So in order to check this, whether true and false are equal, it uses the default implementation, which uses again the default implementation of equality. So it's permanently like caught in this infinite loop here. But the compiler doesn't know that. So you have to be careful there. But there is a way to at least get a warning. I mean, if I did this, I mean, if I removed it and compiled, I did get warnings, but that was for other stuff. So it has nothing to do with this. There is one last thing to say here, but I always forget the syntax. Yeah, okay, minimum. But I never know how to do this, but we just saw it on Hackage, so I can cheat and look there. This here. if we look at the source, we can actually see the source. Okay, I can't because it doesn't let me. Stupid thing. Okay, so now I must guess. I'm not sure exactly how the syntax is. I think so. It's definitely in the class definition. Is it? Does anybody know where that goes? Can I write it above? Let's just check.
It goes inside.
Inside.
Anywhere. It can go first or at first or last, but it has to be inside.
Okay. Thank you, Robertino. And then it's I think the syntax is like this. Right. Let's see. And also this is reflected when I do info, or it's also on Hedok as we just saw. So if I now ask for information, it gives me this minimal pragma. And this means I don't have to implement both, but the one or the other. So this is or. And now if I do what I did before again and remove this here, I mean, it still compiles. I mean, it's still not an error, but now at least I get the warning. No explicit implementation for either equals or not equals. So this is now because of this pragma here. So this is, I mean, how it's also implemented or done in the prelude. So both have default implementations, but because of this minimal pragma, you are warned if you don't, I mean, if you don't give any implementations like here now. So it tells you to do at least, I mean, one or the other or both. And yeah, maybe you may ask, why is this not equal even there? I also have always wondered, I mean, I've never seen a case where that actually was used. But the argumentation is always, or the reasoning always goes that it's sometimes more efficient to check for inequality. I mean, there may be more efficient implementations of inequality than just using the default one. So maybe someone can shortcut, it can be faster to do something special. Okay.
It might be possible that EQ doesn't have the not equals inside anymore in the future.
Oh yes, there's a proposal. Right. There's a proposal. I mean, Haskell is still evolving. So with every new GHG version, I mean, it changes a little bit. And that is one of the proposals, I think. Robertino is right, yes. That, yeah, that they will remove that from the equal class, the non-equal. And I mean, then you could, I mean, we could do that now. I mean, because this is not the official one anyway. So the proposal is to do something like that, get rid of this method, and then also don't need this anymore. And then just define unequal as a normal function. And exactly like, sorry, the default makes no sense anymore then. And then we can just define it as not x equals y. So that's a proposal. So to remove it, I mean, that class equals only as this method, and then not equals is just defined as not equals. So yeah, that's the proposal. And maybe now that I think that's mentioned later in the lecture somewhere, but now that we are on this page, there's documentation here, and there are these properties. It says, for example, equality should be I mean, it should have reflexivity, symmetry, transitivity, extensionality, and negation. So a thing should be equal to itself. If x equals y, then y should equal x. X equals y and y equals z, then x equals z. And this extensionality is x equals y, and you apply a function f to x and to y, then it should also be true that fx equals fy. And finally, this negation thing. This is still for the where, yeah. And sadly, the compiler can't prove this. I mean, we could give an instance. I mean, we can, for example, do. I mean, we could write an instance eq int where equals 42 equals everything, and I mean, I could write that and the compiler would be happy. But of course, that doesn't satisfy these properties. So for example, reflexivity, that x should equal x. I mean, with this definition, if I have 7 equals 7, sorry, is false now with this stupid definition. But the compiler can't help me here. And this is called laws, or laws of a type class. So sometimes type classes come with laws, like the eq type class comes with these laws. And that's something that the compiler can't check. So you can write so-called unlawful instances. But nevertheless, the compiler accepts it. And the way it works is normally you as an instantiator of a type class, so if you write an instance for something, you are expected to check the laws hold. So the compiler can't help you with it. So basically, you are supposed to take pen and paper and prove that these laws hold. I mean, very few people do that in practice, that they take pen and paper. But what people do, I mean, at least I do it, is to think about it, whether that makes, I mean, whether they will hold. And I mean, of course, the more experience you get, I mean, some things are more or less obvious that then works. But anyway, so that's the idea. You are supposed to check, convince yourself that the laws actually hold. But that's like an informal thing. I mean, it's not machine checked. It's I mean, the author of the type class writes down the laws, and then the implementer of the type class, the instantiator, checks them. And of course, nothing can stop you from not doing that and writing unlawful instances. And that's normally considered very bad style, because even though the compiler doesn't check these things, people normally expect that all the instances are lawful. So if you publish a library on Hackage where you invent some new types and you implement eq those types, and now people use your libraries, then they have a right to expect that, for example, reflexivity holds. And they would be very surprised it doesn't. But nobody can stop you. And there are also some legitimate cases to write unlawful instances. And maybe we'll get to that later at some point. But then normally the expectation would be that you clearly document that and write, this is an unlawful instance for this and this reason, you think that's okay. Right. So that's that. I think there's some remark on law of laws, but right. But not, I just want to do this now. Okay, and classes and types are two different kind of fish. I mean, classes are not types. So something like this or that just wouldn't compile. Because I mean, bool is a type, A is a type, but eq A is called a constraint. It's not a type. So that doesn't make sense. So constraints always appear on the very left-hand side and then with these double arrows. Right, and this I think is obvious, I hope. So if you have this signature, then, I mean, both arguments also have to be of the same type, both of type A. And if you want to write a function where you can have two arguments with different types, then it would need signature like this with A and B. And then maybe constraints for both, like in our example. Okay. Right, let's see. Let me just briefly check what all is coming. Certainly won't get finished today, but I think I can start a bit with the important classes, and then maybe we can have another short break, because I think we already talked about this in the first lecture about some examples of type classes. So now we have talked about equality. To check equality and inequality, and it's so-called structural equality. So it's not, I mean, in some languages you have equality for everything, and that's then sometimes done with pointers. So it checks whether basically an object also is the same thing in memory. So the memory pointer is so-called pointer equality. So that's not what Haskell does. It's so-called structural equality. So it looks how the values are constructed, and then if that's the same. I know in languages like C#, so on .NET, I don't know whether any of you are familiar with that, but there somehow you have both. So, for example, objects in C# are compared with pointers, but you also have primitive types like numbers or characters and so on, and they are that's not point equality, it's structural equality. So it's a bit complicated in .NET. Anyway, and as we have seen when I showed it to you on Hackett, I had to scroll very, very, very long down to, so there are lots and lots and lots of instances for equality. So in principle, basically all core types have an equality instance. But there's one notable exception, and it's function types. So you can't compare functions for equality, which makes sort of sense because, I mean, the compiler can't, I mean, it's basically an impossible problem. What does it even mean that two functions are equal? I mean, you could take the mathematical approach, two functions are equal if for the same input they give you the same output. But that is, I think, probably impossible to check that automatically. I mean, if I give you two implementations of functions that behave the same, it may be very difficult to see that from the code, how I implemented that. So functions you can't in Haskell compare for equality. But most of everything else you can. Okay, then there is OR. And this is sort of defined like this. And here we see something that we probably haven't seen before. So this means we define class OR on A, and it's sorry, superclass. Eq is a super. And this is read that Eq is a superclass of OR. So that means in order to be in OR, an instance of OR, A also needs to be an instance of Eq. So everything that's in OR is also in Eq. That's what this says. And similar to Eq, there's lots of redundancy here. So, I mean, we have the usual comparison operators, but, and there's also max and min, and there's compare. So that looks a bit weird. So we have two A's and it gives you ordering, and ordering is defined like this. So ordering is a type with three values, LT, EQ, and Q and GT with the obvious meaning. So less than, equal, greater than. So you have this, I mean, I can demonstrate that if I do compare, example, 7 and 42. I get LT less than, so 7 is less than 42. If I do 5, then I get GT. 7 is greater than 5. If I do 7, I get EQ are equal. And if we look at information on the ORT class, we see lots of instances here. And basically what's on the slides. And we also see that as minimal definitions, it's enough to just implement compare or just implement less than or equal. So typically, if you write an instance, then you only have to define compare or this less than or equal, and everything else has default implementations in terms of those. Okay. So this syntax is new, and it means eq is a subclass of odd. You cannot, I mean, in order to give an instance of odd, you first need to give one of eq. And also the converse is true. So if you have a function that has an odd constraint, then the compiler knows that that also implies eq. So if you had a constraint like this, then this eq wouldn't be necessary. You could leave that out because odd implies eq. And some people, I think, complain that the error is this way around. And I think in some languages like PureScript, it's actually the other way around. Because, I mean, in mathematics, normally this error is like implication or in logic, and it's somehow the wrong way around. So odd implies eq, not eq implies odd. But it is what it is. Right. Okay, so that's eq and odd for comparison. Eq for equality comparison, odd for like total ordering, less than and greater than. And odd, again, lots of types are already an instance of odd. So in particular, string, I mean, lists. I mean, if I ask for information here and we see, for example, this, so if A and B are orderable, then also pairs of A and B's are orderable. And that uses lexicographic comparison. So if I have, let's say, for example, if I use characters and ints, so if I have A7, then B42, and I must give notation. So that's true, fine. But if I have 2 here, the first one is still less than. So it first looks at the first components and compares those. But if those are equal, then it looks at the second component. Right, that's what is normally called lexicographical comparison. And it is called lexicographical comparison because we have the same for lists. So if A is a list, you can also order a list. It's called lexicographical comparison because that's in a lexicon, a word book, I mean a dictionary. Because in a dictionary, words are sorted alphabetically. So it's another word basically for alphabetical. And because we know that characters are in odd and strings are just lists of characters, and we just saw here that if something is orderable, then also, orderable, then also lists of that are orderable. So that means strings are also orderable, and they use lexicographical comparison. So I can, out of the box, I can compare Kenya and Nairobi. And that's true because in the lexicon, Kenya would be before Nairobi. So it starts comparing first characters, and K is already less than N. So that's why Kenya is less than Nairobi. If the first 2 characters were the same, then it would look at the second characters and so on. Right, so that's the odd class. Then we have show that we already talked about. That's mostly useful for debugging or in the REPL, that you can actually show the results of computations. And technically, it's just a class with the method show from the type in question to string. And the REPL, for example, uses that. So implicitly, when you ask the REPL to evaluate a Haskell expression for you, so for example, this one. So the result is bool. And then the REPL calls show on bool to produce the T, the R, the U, and the E to display on the screen so that it can show the result to me. So if I had something of a type that's not in show, like a function, then the REPL can't show it to me. So if I, for example, have the function that takes the X and the Y and addition, I will just write this, then I get errors, no instance for show of this function type. And we see that actually it's more complicated, so it doesn't have only this show method. It also has this show spec and show list. So list is to handle things like string. I mean, let's, I mean, it's not really important, but let's say I have a list of booleans. So, I mean, true, comma, false. I mean, this is displayed like that. So square bracket, and then, I mean, the show of the first element, then a comma, the show of the next element, and then closing brackets. But if I do this, so the list with two characters, X and Y, then it's displayed differently. It's displayed as a string with double quotes. So there's special, I mean, not all lists are showed in the same way. So this is the default behavior basically for lists. So it just does the square brackets and then shows element, first element, comma, second element, comma, and so on. But in the special case that we have lists of characters, then it's not displayed this way, it's displayed that way, to make it nicer to display strings. And so that is what this show list is used for. So for the character instance of show, there's some special treatment of characters. But that's, yeah, it's basically just technicality. And the show spec is used to do precedences. So if let me see, is there an example I can, not sure right now. Have we seen enough examples for this? Yeah, yeah. Maybe with either something. If I have left C type either. Right now, around this, I mean this, but if just have left C, so here you see if I just have this left of the character C, it's displayed like that, left C. But in this term here, it has the parentheses around. And that's what this, so it's displayed differently depending on like its position in maybe a larger term. And that's where this preg for precedence is used. So for also, if you want to display like expressions, arithmetic expressions with additional multiplication, and you want, I mean, then it gets complicated, right? I mean, you could write 3 + 4 or something, but if you want to multiply it by 5, then suddenly you need parentheses because this would have a different meaning. And that's what this show preg is for. But you normally don't have to worry about that because the compiler can automatically write instances for that. And it's also enough so for easy, I mean, for quickly implementing something, show, I mean, in the minimal definitions, you can just give show. So that's also fine. And I just said, so the REPL uses show to actually display results to you. And if something doesn't, then you get an error. I demonstrated that. There's also now a class that we haven't talked about yet, read. It's like the opposite of show. That's also used by the REPL. When I type stuff, I mean, when I type 42, that's a string, right? It's 2 digits, 4 and 2 characters. But somehow this must be turned into the number 42. So the read type class has something, I mean, that's also complicated due to this precedence stuff. But it doesn't really matter. Important is that once you have read, you have a function called lowercase read. Given a string, turns it into an A. So this can be used for parsing. So for example, I can try that out and I can say read the string 42, type int, and it works. So it takes this string and parses it as an int. But if I do something like bool now, then I get an exception, read no pass, because it can't pass the string as a Boolean. But if I do this, then it passes it as true. So that's read. Right, and it comes, I mean, I had to give annotations, but I don't always have to, so I can do, for example, this. The compiler can figure out automatically that I want a Boolean here because I am using logical disjunction, and it knows that then the first argument must be of type bool. So it can automatically infer the type here. Okay. And sometimes it can't, so there is this example here. So we can try it out if you want. Strange x equals show read x. So from string to string, and we see it gives an error. And why? Well, because even though this is a perfectly reasonable type, something from string to string, and read works on strings, and right, but the compiler has no way of knowing, I mean, what we want to do here. So for example, maybe we want to read it as an int and then show that int again. But we could just as well want to read it as a Boolean and then show that Boolean. So the compiler doesn't know which read instance to use here, and accordingly which show instance. Because this intermediate type that we first pass the x to and then show it from, there's no way the compiler can know that. And we could give an annotation and then it would work. We could do something like this. Now the compiler knows that we want to pass it as an int and then show it again. So now if I do something like 42, it actually works. But it wouldn't work for things that can't be passed as an int. Right. And I showed that works, and that also works, but I must somehow tell the compiler which of those to pick. Let's see what's the next. Yeah, this is just, I mean, this sometimes happens. So if you have, I mean, the problem here is that both show and read are overloaded, and go here, overloaded. So the compiler can't figure out the type. I mean, read is from string to A and show is from A to string. And that fits together, so far so good, but you can't in the signature of strange, which is just from string to string, this A doesn't appear. So the compiler has no way of figuring it out. That's this several overloaded functions are combined such that the resulting type does not mention any overloaded variables anymore. You have to specify the intermediate types manually. Let the type checker resolve the overloading, like I did here with this explicitly saying it's supposed to be int. Right, and so that looks a bit painful, especially this show and read, to do that by hand, but luckily you very rarely have to, because the compiler has special treatment for certain classes. So there's a relatively short list of type classes the compiler automatically derives. So eq, odd, show, and read are on that list. So you never have to write an instance for one of those 4 classes by hand. You can just use deriving. So so now I should probably switch to a different file. Was there a question?
It was?
Oh, sorry, I heard some ping. I thought
Yes.
somebody.
Yes, someone, I think he's trying.
Hello.
Hello.
Oh, sorry, it wasn't a question. I was looking for the thumbs out to appreciate that function. Yeah, I really love that. Sorry for interruption.
No problem. Okay. I Just what did I do now? No, nothing bad. I just want to start a new module because I'm hiding this this eek, and that's a bit painful. So now I want my eek back. So if I do, I mean, we have seen this tree type before. Leave a node tree A. So I can just do deriving show read odd, and if I always restart the REPL if I change them, but I'm not sure. It's in this case it seemed to work. Anyway, so now with this line I have instances now automatically derived for show read eq odd. So we can try that out. So if we have an example tree, it's a tree, let's say, of character, why not? Let's say node if x node if c, something like this. So if I now, I mean, it can show it to me because of the show instance. And I would also be able to pass it back. So for example, I can say read leave true type tree bool, and that also works. And let's say equality, so I can do leave, I don't know, false equals leave true, false, and true. And odd, I mean, somehow these are now also ordered. So for example, leave false is not less than itself, but it's probably less than, yes. So these automatically I get instances. Because it's not so obvious what they actually are for odd. But normally it's always sort of lexicographical, whatever that actually means. So probably leaves are always less than nodes, and if both are nodes, then, I mean, if both are leaves, then the A will be compared, and if both are nodes, then probably first compare the left subtree and then the right subtree. That's something like that. But you get that automatically out of the box by just using deriving. Right. So actually, I think we should have another break. I just want to say that this is, I mean, there is Haskell standard, Haskell 98, and I think that is written in the standard that there's a list of 7 type classes or something, and that the compiler must be automatically able to derive them. And now we can also look, I mean, we can, if we ask for information on tree, then it shows us tree and the constructors, but it also shows us these instances. So it says, I have equality on trees provided I have equality on A's. I have ordering on trees provided I have ordering on A's. I can read trees if I can read A's, and I can show trees if I can show A's. So all of this the compiler has automatically figured out and derived. But there's this relatively short list. So there are a couple more. I think it's 7 or so in the original, but basically mostly these. These are the most important ones. And hopefully in a later lecture, I mean, this is a bit, I mean, it's nice, of course, but it's a bit sad that that is like hard-coded in the compiler. So, I mean, it's those 7 classes that have this luxury of being derivable. And if you define your own classes, for example, then you are on your own out in the cold and have to write your own instances. And but as we will see later, there are mechanisms in Haskell that allow you to basically provide something like deriving for your own classes as well. It's called a generic program. So a lot of so typically nobody spends a lot of time writing instances, because for most common classes, also on Hackage, with various techniques that some of them will see later. It's normally always easy, always an easy way where you basically don't have to write any code to get your instances. Okay, so I think we should have another short break, maybe 10 minutes this time, and then we can talk about numbers, except if there are any
Okay.
questions. Okay, then 35.
Okay. Sure.
Okay.
Okay, talk to you then. Okay, let's talk about numbers. Numbers. So Haskell has a lot of numeric types and type classes. So here in this table on the left, that's some of the available types in Haskell, and then what instance they are of. So all of them are instances of num. That basically makes a type a number. Then you have like a whole zoo of other so-called numeric type classes, like integral, fractional, floating, real, frac. So num is a superclass of all of them. And it's also a superclass of integral. So in order to be integral, you need to be num. And fractional is a superclass of floating. And so, I mean, let's look at some of these types and some of these classes. So int, I mean, is bounded. So there's a smallest int and the largest int. And I think I think I mentioned that before, the standard leaves that open how large. I think it says it must be at least 16-bit or something. But I think nowadays, basically everything uses 64 bits for int. You can actually ask for this in the REPL. So there is this enum class that I briefly mentioned. No, sorry, the bounded class. I mean, enum is there as well, but there's the bounded class. And the bounded class has two methods, minbound and maxbound. And int, for example, is an instance of that. So we can ask for minbound of int and the maxbound of int. So it's large. It's like, I think 19 digits or something, 64 bits. For most, I mean, simple applications, that's already good enough. Then there's also integer, the integer type, and that's unbounded. So you can have arbitrarily large numbers. So for example, we could define factorial, the factorial of a number. So from integer to integer, or let's say from A to A, just num, sorry. So the factorial of 1 is what, of 0 is 1, and the factorial of n is n times the factorial of n minus 1. All right, because I'm doing this case split here, I also need equality, because in order to check which of the equations applies, I must know whether the number is 0 or not. So I also need an E constraint on A. And actually, strictly speaking, I mean, this is not complete. So I would also say something like n less than 0 error factorial of negative number. If it's equal to 0, then it's 1, and otherwise. Okay. And now I even need an odd constraint. Anyway, so now I have this factorial, and now I can, because of, okay, fine. Doesn't matter. So I also need show because I'm showing it in this error message. Okay, so now that I have this, I could, I mean, factorial of -3. it's an error, and I get this negative number, my error message. Factorial of 0 is 1, and go on. Okay, but if I now go overboard here, know how far. Okay, then it like gives nonsensical results. So at this point, it has somehow overflowed, and suddenly I get a negative result, which of course doesn't make sense. So now I hit the upper bar. I mean, it comes too large. So now the factorial of 30 doesn't fit into 64 bits anymore. But this is no problem if instead I use integer, and they can be really, really large. So I can give the factorial of 3000 or something. Okay, and while we are in the REPL, so num has plus, minus, I mean, addition, subtraction, multiplication, negation, absolute value, sign, and a way to convert from integer. And we also see like the minimal. So for example, you don't need to define negation and subtraction. One of the two is. Okay, then on the slides was also mentioned integral. So this has stuff like with integer division and so on. I think I already demonstrated diff and mod diff at some point. For example, you can say diff 13.3. So that's 4. So 3 goes into 13 4 times, and there is a remainder of 1. So with mod, you get the remainder. Then there are also variations like diff mod, where you get both of them at the same time. Right. So that's integral. So then we also have like fractional numbers. So we have floating point. So something like pi, and pi is something again. So let's like this. So there's double. That's double precision floating point. We also have single precision floating point, but that is very rarely used. So there's very seldom a good reason to not just use double. We don't have anything equivalent to an integer, so like arbitrary precision double floating points in the standard libraries, but there are, but there are on Hackage, there are like somewhere you can do like very high precision calculations with hundreds of decimals. And we have rational, so we can do something like 3 divided by 5 rational, so rational numbers. So they use integer. So the numerator and the denominator are integers, and the what's that word in English? I mean the fractional. The fraction is this percentage sign. So that's 3/5. And I mean, you can, of course, do arithmetic with this. So 3/5 plus 3, I don't know, plus 1/3. So by default, it assumes I'm meaning rational, but sorry, double. But if I say I want it as a rational, then it does calculation. It's 14/15. And because it's integers, that's also then arbitrary precision. So arbitrary precision rational numbers. That's actually quite nice. And that's an instance of the fractional type class. And fractional gives you in particular the slash for division. Then we saw that there's more in this zoo of type classes. So we have talked about these now, int, integer, float, double, rational. There's also floating and real frac. And I always forget what they do. So floating has floating has these trigonometric functions and logarithm and so on. So pi, exponential function, logarithm, square root, sine, cosine, and so on. So in particular, rational is not an instance of this, but double is. So I can do, for example, pi type double. or of type float, but not of type rational, because it's not an instance of floating. Right, and then there's this real frac.
Lars,
Yeah. Question?
Adrian have a question, so go ahead.
Yes. What is the difference between float and double regarding the number of bits that they have?
I mean, float uses half as many. I mean, but I think float is 8-bit and double is 16-bit, I suppose. You can check. Yeah, that doesn't really help. Let's see. Here. Okay, float. I mean, it just says IEEE single precision and double is IEEE double precision. But I don't know what that means. I mean, I don't know. I mean, it's the standard thing you get in many languages. I mean, we could just IEEE single precision. Okay, that's 32 bits. And I think double precision is 64 bits then. Okay, yeah. Okay, fine. So that's 32 bits. And I think double precision is probably 64, if I'm not mistaken. Yes, yeah, here it says. So 64 is double. Okay, so it's 32 and 64 bits.
Okay, okay. Thank you.
Welcome. But I think that I only know one library on Hackache that uses float. I mean, most everyone uses double. Okay, and this real frac is somehow, see, it has this real and fractional as a superclass, and what's real, that's not even mentioned on the slides. Real is you can convert it to a rational function. So we could do 2 rational of pi type double, and then it gives us some sort of rational approximation of pi. And real frac then, in addition, has things like truncate. So given some integral or ceiling and floor. So I can, for example, take truncate pi type double to an int, and then I get 3. So yeah, there are lots of functions, and some, I think that's on the slide. Sorry, where are we? Right, so this is like the standard, the basic arithmetic operations are in num. And in particular in num is this, if we look for num again, there was this from integer function. So it takes an integer, so you can convert an integer into every numeric type. And that is actually used by these overloaded so if I ask for the type of 42, then it tells me 42 is of any numeric type. And the way that's actually done is using this from integer. So 42, the literal 42 basically gets parsed as an integer, and then using the from integer method of the numeric type in question, it converts it into that type. That's why I always, when I do examples in the REPL and I want to do something simple like to add 2 ints, then if I do 42 plus 7, I always get this annoying warning that it doesn't know which type I'm talking about, because it could be any numeric type. And then it always says it just by default for the REPL, it assumes it's integer, and then it gives me the result as integer. That's why I always did these things like annotate that I'm talking about ints, and then this warning gets away. You can also switch off that warning, but I know you don't. Right, so that's how that is handled. And fractional, if we look at fractional again, that has this from rational function, and that is used to parse like decimals. So if I mean, the type of 42 was, it's for every numerical, but if I ask for the type of 3.1, it's of type A for every fractional A. So I couldn't do 3.1 of type int, that gives me a compiler error, but I can do 3.1 of type double or of type rational. And then it's 31/10. So it's one thing. There's, I mean, numeric literals in Haskell. So if you write a literal number, they are overloaded. So without a decimal point are literals for every numeric type, and those with decimal point for every numeric type that is an instance of fractional. And I mean, Haskell doesn't have any implicit coercion. So I mean, in JavaScript or in other languages, often you can, I mean, you can, if you want to add an int to a double, then a lot of languages, the int will simply silently be cast to a double, and then the result will be double. In Haskell, that doesn't work. You can't do by this, then it says you can't add an int to a double, because the type of plus, I mean, if you ask for the type of plus, it expects the same type on both sides of the plus sign. So what you have to do instead is you have to explicitly cast. There's a very useful function. I mean, there's this from integer. There's also one that's called from integral. So that can convert from an arbitrary integral type to an arbitrary number type. And as we saw, integral, I mean, the most important examples are int and integer. So it can, for example, take an int and convert it into every numeric type. So if I want to do this here, add an int to a double. So let's just give them names, int, and let's call it 4.2. So as we saw, I can't just do this. So if I want to add them, then I can do from integral for the 3. So this will convert the int 3 into a double 3, and then it can add it to the 4.2, and I get 7.2. So this from integral is often used. So if you do like numeric calculations in Haskell, then often it looks a bit ugly because there are a lot of from integrals there somewhere. Okay. Well, we went over those. I explained this. Right. This is an interesting question. So let's see. Can I do 3.2 times 2 and expect a double? Yes. But can I do 3.2 times, what is it, 5 diff 2? 5 diff 2 and expect a double? No. The reason is, I mean, why is this okay? Well, if I want a double, we have seen the literal 2 can stand for every type, so every numeric type, including double. And 3.2 can be of every fractional type, including double. So if the compiler sees that and I want double, then it can pass both the 2 and the 3.2 as doubles, and then it can multiply them, and that's fine. But here, the diff is only defined for integral types. So this 5 divided by 2, no matter what I do, I mean, it's an int or an integer, but it's an integral type. Whereas the thing on the left-hand side is a fractional type. So if I want a double, then it's fine for the 3.2, but this can't be a double because double is not integral. So if I want to make this work, then I would need to explicitly again do a from integral here. Now it wants again this integer thing, but for example, if I do from integer, then one goes away. So then it will compute this as an integer, which is 2, the integer 2, and then convert that. The from integer will convert it to double, and then it can multiply it with the 3.2 to get 6.4. So yeah, that takes a bit to get used to working with these numeric types in Haskell. That's also not too bad. And it's very explicit. So, I mean, in other languages, sometimes it can be surprising when you I mean, in JavaScript, for example, I never know what happens if I mean, if I divide, does it, yeah, I mean, if I divide 2 by 3, for example, in JavaScript, I'm not really sure. I'll probably get 0.66666. But I mean, here you have better control. So it doesn't do anything, any coercions automatically. You have to be explicit about the types. Right, I explained that. I explained this. So this is very versatile function that's used all the time because it can convert any integral number, so in particular int or integer, into anything else, everything else. And I already briefly showed you those. So we have floor and ceiling, so rounding down, rounding up, or rounding. So if I do this with, I mean, like, sorry, let's define Euler's number as x1 type double. So that's that. And now I can, so I can do floor. It's 2, and I can do ceiling, which is 3, and I can do round, which in this case is also 3 because it's closer to 3 than to 2. But if I round pi, then it's 3 because 3.14 whatever is closer to 3 than to 4. Okay. Okay. I think we should probably stop before let's see, there's not much left, but we should continue. Yeah, so this is just a recap. Or maybe, yeah, okay, there's this. Okay, we can maybe quickly go through that because that is only 2 slides. And then we do the higher order functions next week. So what do we have seen so far? So in the examples, we saw, for example, int and character functions, of course. So they are really truly built-in types. So types that are not defined in some library but that are really built in. So int is built in, and character is built in, and functions are built in. Then there are functions that you could define yourself, but that have special syntax. So we saw that tuples and lists have special syntax. These parentheses for tuples and the square brackets for lists, they are, I mean, you couldn't do that yourself. So that's the compiler does something special for those types. But in principle, apart from this, what they look like, I mean, the syntactic sugar, you could have defined tuples and lists itself. Then there are types that are in the prelude. So they are defined, but they are basically always available. So they feel like built-in types. So example of that is bool, maybe, and either. So bool, for example, is not built in, and it's also doesn't have any special treatment. Just somewhere in one of the base libraries, it's just defined as data bool equals true or false, and similar for maybe and either. And then there are types that are just names for other types, like string, which is just another name for a list of character. And then, of course, there are types that you define yourself. And we have seen data, new type to do that. And I've demonstrated this, that :I, you can quickly get information about a type. So you see the constructors and you see what class classes the type is an instance on. And I mean, if it's, I mean, as we saw, if we ask for information on a type like bool, it will give us the constructors, in this case, false and true, and it will give us the instances that bool, I mean, is an instance of, the classes that bool is an instance of. So we see bool is bounded, enum, ort, read, show, eq. If you ask information on a class like eq, then it also gives you the definition, the methods, and the ones you minimally need to implement, and it shows you types that are instances of this class. So we see, for example, that if A and B are instances of eq, then so are pairs, and so on. or we see that integer is an instance of eq, int is an instance of eq, and so on. So this I is very useful. Okay. Okay, and if we try this, so sometimes I shows more than we wanted to show. So we see that actually int is, it was a lie to say that int is built in, because actually int is defined as something that looks horrible here, something very cryptic. So even int is not really built in, but there is something, this is basically, this thing here is like a machine integer, like really hardware, a hardware number. And this int is like a slightly complicated wrapper around that. We will talk about that briefly in another lecture, but it's not very important. Okay, so I think we should stop here. Are there any last questions?
Not in the chat.
Okay, and if there are no questions, we talk on Wednesday. Is there anything still to say to the assignments, Robertino or Karina? I suppose we publish the next one today.
Yeah, actually, the next one is higher order functions.
Oh, okay.
Yes.
So then we don't.
So they have time until next the next lecture to finish the one that we publish on Friday.
Okay, that's good. Okay.
And, yes, 1 second. Katrina asked, where are the slides you are presenting? And we have this the repository, and that we shared a couple of times. We can share it again, and we publish them after the lecture.
Yeah, let me share. Let me just, sorry. Let me share my screen again briefly. So if we, is that the right one? No.
Yes.
Yes, okay. So this is the repository for the class, the GitHub repo. So github.com iog-edo-kenya -2024 cardano-dev -2024. And there's everything. I mean, that's like the main entry point to the class, with lots of, like what we talked about last time, how to install everything that you need and so on. And then here it's missing at the moment. So why is it
It's
not
in the
there?
folder. It's a folder.
Ah.
Not linked.
Oh, it's not linked. Okay, sorry. Here's this folder lectures. And there are the lectures. So the one from today is still missing, so we'll add that today. So this was the one from last Friday. And I think Anderson always on Telegram, he publishes links to the recordings as well. So these are the slides. We can of course link it, but yeah, okay. We could link it here as well to that.
Yeah. Okay. I will link the old lectures. Yeah.
Thank you. Yeah, okay. Any other questions? Okay. If there are no other questions, then I'll see you on Wednesday. And
I have a question.
yes.
I don't know if I'm repeating a question that has already been asked, but my question is committing or adding changes to our own repositories, is it submitting assignment? Do we submit assignment by committing changes to the assignment?
I think you must push, right? What, you know?
Yes.
Yeah.
So
Yes,
by-
Can you push more than?
You can push multiple times until the deadline.
Oh, okay.
As many times as you want. Yes, and it's encouraged. So you like just in case, like just keep committing and pushing with like good messages, Git messages.
Okay.
Yeah.
Right, but you push. So committing is not enough. You must push.
Okay. And also, I had some challenges with setting up my VS Code. I've been having some challenges for quite some time now because I put up Docker. I don't know if it's me who did not understand, but I put up Docker, and when I tried running code in VS Code, it was saying that it does not have it does not have, I don't know how to put it, the editor to compile text.
Could you share maybe in the Telegram chat a screenshot of the error? You have to have that Docker desktop installed, VS
Can I
Code, and the extension.
share my
Yes,
screen
yes, you
now?
can share. For sure.
Yeah, let me stop presenting. Are you trying to?
Yes, I'm sharing right now. So as you can see, I created 2 files, and then as I was trying to run the code, or basically the code that you gave us, as I tried running the code, this is what it has.
No, you can't run it like that. I mean, you must open a terminal. If you go to terminal, upstairs, I mean, there at the top left on the right to run, there's the word terminal. Right top, the top bar. There, no, on the left,
Or left part.
there it says terminal.
Um,
No, up at the topmost row, a bit further to the right, right, a bit more right there.
or terminal.
New terminal.
Okay.
And then once the terminal opens, you must type Cabal. Well, sorry, but you must first go in the right folder. So CD into 02.
CD into GitHub
Zero-
Plus.
It's called 02, I think, 02 something.
02. Oh, okay.
And it's just tab, no, 02 tab to get completion. 02.
Should I copy?
No, you can just type 02 and then tab. Tab. Did you tab?
Yes.
Not the enter, the tab.
Not enter, tab.
Oh, tab. Okay.
Now enter. Okay, now you can do Cabal REPL.
Yeah, but I think Tribe is not going to work because it's out here outside the.
Or outside the container.
Yeah.
Okay.
Because it's C colon, that's Windows.
Oh, I see.
And so can you run there, like where you are instead of Cabal? Can you run code dot?
Can I run the code?
Code CODE space dot.
But he's already in code. Okay.
Yeah, but it's going to open a new, and it's going to do the prompt.
Okay. Can you a dot and enter? Okay.
A folder containing a dev container configuration file. Should I reopen in container?
Yes. It opened in a different.
So we can't see anymore, but
The notification has gone away.
Click on the corner. Yeah, click on the corner bottom right, and you can see the notification again. You can accept it, but we cannot see because you shared VS Code, the VS Code window specifically, not the whole window, so we cannot see what you're doing now.
Okay, let me share the whole window.
Sure.
okay.
The notification has gone. It was here.
Look at the bottom right. You have a bell icon. No, not in the new VS Code that you just opened. There, you're
Oh,
almost there. A bit to the right.
Oh, okay,
There.
okay.
Click
There
the
we-
opening content. Yes. Okay, you have to open Docker desktop. You have to have it open, running.
It
Just
has.
if you open the app, that's it.
So, one guy, please.
Yeah, I was trying to
I'm
follow
in chat
follow the
operator.
instructions on the GitHub, but it was saying settings, preferences, and when I open my Docker engine, I can't see all that. That's why I was stuck.
Okay. So now we wait a bit for the Docker engine to initialize, and then when you click on the opening container, it should open correctly. It will take a bit to download the images, but it should open correctly, and then you can run what Lars was saying, Cabal REPL or Cabal run.
So at any point I want to run a code, Docker must be open.
If you're on Windows,
Yes.
yeah. If you're on Linux, of course, it's much easier, but anyway. Right, so now you can go back to Visual Studio, to the second one, and try again. Let's reopen. You can also click on the, I think it's the bottom left, is it? This blue icon there?
Yes.
Yeah,
Not sure
it's
it's
the
going
bottom
to
left,
show
the
it.
blue square.
Yeah.
There's a blue icon on the very left corner. There should be something.
Reopening
You
container.
can, yeah, exactly. And now it will take forever, but only the first time. You can click on this blue show logs, and there in the notification window it says reading dev container configuration show log. You can click on that if you
One
yeah,
guy.
yeah. And now you see what Docker is doing. It's downloading the software now. So that takes a while, but only the first time. Once you have done it once, the next time is much faster.
Oh, thank you very much.
Yeah, one guy.
Okay.
I will chat you up on Telegram, please, so you can push me through the process.
It should be.
Según you said that you want help in Telegram.
Yeah,
Okay.
I will chat you up on Telegram.
Okay, perfect. Sure.
Yeah, so you can walk me through the same process, because I've been trying to do these things. I'm not getting it.
Okay, so yeah, this will take a while now. That will take a couple of minutes, but it will only hopefully be the first time. Or is it already done?
No.
Okay.
Now it's opened now it downloaded the Ubuntu image, and now if you click again in show logs, you will see the whole setup that we prepared. Like now it's the actual Haskell installation inside the Ubuntu container.
Right. So you see there it's doing some steps, and some of them will take a while. But if
So
you're patient, then
it's taking a long process for it to run.
yes, it is, but only the first time. So once it's done once, the next time it will be much faster because it caches it.
All right.
Yes, this time is well, like we're installing like all the tooling, the compiler, the Cabal, etc. And then like next time you open, it will see Docker that it's already, everything is already downloaded, installed. So it's just going to open the container you have, the image that you already have.
Understood.
And then what I wanted to tell you earlier, if you then CD into the right folder, and then you can do Cabal REPL, for example, and then the REPL opens.
I can do Cabal and then the name of the file.
No, Cabal space REPL, REPL.
REPL. Got it.
I mean, if you look at the recordings, I do that all the time. You must just look at one of the recordings that Anderson shared.
Yes.
Okay. I think maybe if someone else has a question, because this is going to take a bit, and better to just, instead of waiting 15 minutes for it to download everything, we can.
Yes, let me just, I just grab it again. I just want to show, so where, I mean, you basically let me close everything here. Sorry, so, yeah, okay, fine. So now this is where you were basically. So it will look, and the path will look different. I mean, you saw your drive and some path on Windows. When you reopen a container after you are done, it will look something like this. So with different names for the folders and so on. But now I'm in this folder, and now I CD into 02, for example, enter. So now I'm there, and now I can just type Cabal REPL, enter. And now I'm in my REPL, and now I can do Haskell.
Thank you so much.
Very welcome. Okay. That's that. Okay. Anything else? Okay, then, and yeah, if anybody else is struggling with that, I mean, you can also post screenshots on Telegram or something. But normally it should, I mean, it works. You just need some patience the first time. But as we said, the second time it's fast because it only has to build all the tooling once, and then you have your image on your machine, and then next time it's just available. Okay. I'm afraid I have to leave now because I have another meeting soon. I don't know
If someone else has questions, we can like troubleshoot on Telegram with screenshots, or we can, if needed, we can like create a specific call with someone and do like troubleshooting live.
Okay.
Okay.
Great. Then thank you very much, and I'll talk to you on Wednesday, and yeah, we can communicate on Telegram. Okay. Thank you. Bye for now.
Bye. See
Bye.
everyone.
Thank you.
Goodbye.